for the diesel cycle, we should be able to sketch a pressure volume diagram as well as a temperature entropy diagram. Let's do the pressure volume diagram. This is true also for a piston cylinder Otto cycle. Think of lining up the cylinder at the bottom of your diagram. Think about the piston being out here, and that would be the largest volume, the volume at bottom dead center, and so you line it there, and then the piston would have low pressure in the gas inside, and then if it moved, it would move to a position where it's at top dead center, the smallest volume, and then you would have a high pressure. Here, after the compression stroke, the piston would move back to a distance maybe about here, undergoing combustion, constant pressure combustion process. That's the assumption or modeling approximation in the diesel cycle. And then it finishes with a expansion back to bottom dead center and then completes the cycle. So we'll start with state 1, state 2, state 3, state 4. 1 to 2 is very rapid adiabatic compression. We're doing an air standard analysis. It's internally reversible. Hence, the property S is equal to a constant during that process. Isentropic compression. And then we have a constant pressure heat addition. So if you wanted to, you say P is equal to a constant. But that's pretty obvious from the diagram, but let's put it anyway. And you're going to add heat until you hit the cutoff ratio. This, I don't know if I lined that up very well. Here, this is V at state 3, this is V at state 2. And so this is the V at state 1, which is equal to the V at state 4 as well. Okay, so the compression ratio for the Otto as well as the diesel cycle is the initial volume at the bottom dead center, state 1, divided by the volume at top dead center or after the end of the compression stroke. Okay, then we have another cutoff ratio, and it's V3 divided by V2. Both of those ratios are greater than 1. So it's a 9, 10, 20, whatever that compression ratio is. Typically for a diesel cycle, it's about 20. And then for cutoff, maybe 1.5 to 3.5, 2.5, something in there. It's not very big. Okay, and now let's continue to do the expansion. If you go from state 3 to state 4, internally reversible adiabatic, and we get that S is equal to a constant. And then from 4 to 1, we have this constant volume heat rejection, or cooling, so the specific volume is equal to a constant. Let's go ahead and sketch it now on a temperature entropy diagram. Temperature entropy. So from 1 to 2, it's isentropic. And then we have the constant pressure, heat addition out to state 3, our maximum temperature. Then we're going to go down to state 4, isentropic. And then we'll have 4 back to 1. Specific volume is constant. So S equal to constant, S equal to constant. Pretty obvious from the TS diagram that they're straight up and down from 1 to 2 and 3 to 4. All right. Is that all a good review? Let's press forward. We want to be able to do the first law and the second law analysis for each of those processes. So for the process, 1 to 2, then 2 to 3, then 3 to 4, and then 4 to 1. We want to be able to write the first law down. The first law in general is U final minus U initial is equal to the Q in during the process minus the work in the process. Now I've written it for going from 1 to 2, but when we apply it for 1 to 2, it's adiabatic, and so the work 1 to 2 is simply U1 minus U2. Did I do that okay? How about we write the general form of the second law for a process? would it be the final entropy is equal minus the initial entropy, so that's the entropy change, is equal to how much entropy is transferred in with the heat, integral del Q divided by T. You can put a B on there because it is the boundary temperature at which it's being transferred in. And then we have plus sigma 1 to 2. So if it's internally reversible and adiabatic, we conclude for the process 1 to 2 that S2 minus S1 is equal to 0. It's isentropic. So that's a big conclusion. Now, last time we talked about this harder process 2 to 3 because 1 to 2 is just like the Otto cycle. It's just a different compression ratio. But now 2 to 3 is constant pressure heat addition. So when we write out our first law, we pick up something like, let me do it this way. How do I want to do that? Is I'm going to get that Q after some work, 2 to 3, is equal to H3 minus H2. What? There's a few steps in there, isn't it? Professor, I think you have an error. I think there's a U. It needs to be U's, not H's. No, it needs to be H's, isn't it? And so it's a change in enthalpy. Why? Because the boundary work 2 to 3 is the integral P dV, and that pressure is constant, and so it can come outside that integral. It'll just be like P3V3 minus P2V2, and then that can be grouped on the other side of the equation with the change in internal energies, such that you get a final amount of heat added is proportional to the change in enthalpy, or it's equal to the change in enthalpy. Okay, so that's the big conclusion. You can do the second law, but it really just says that there's entropy increase because of entropy transfer in with the heat. All right, let's go to 3 to 4. You do the same thing. S4 minus S3 is equal to 0. It's isentropic. And we find that the work 3 to 4 is equal to final state 3 minus U4. And then 4 to 1 is the Q 4 to 1 is equal to U4 minus U1. It turns out to be negative. So if you want, you just remind yourself, this is going to be a negative quantity because it's heat transfer out. This is a positive quantity because it's heat transfer in. This right here, this work 3 to 4 is positive out, and this one is negative in. Okay, right. There is a non-zero work for 2 to 3. So when you do the sum of the Q's to get Q net, that's equal to the sum of all the Q's, and you compare it with W net, which is the sum of all the works, make sure that you include the work 2 to 3. Otherwise, Q net will not be equal to work net. All right. We want to solve a problem. Okay, so we have air at this pressure and temperature at the start of the compression stroke in an air standard diesel cycle. Are we ever going to do a non-air standard diesel cycle? Nope, they're all air standard, meaning there's a bunch of assumptions in it. We're replacing the complex, intake and exhaust stroke. We're replacing the combustion with the just heat addition. So it makes it very simple. It has a compression ratio of 20 and a cutoff ratio of 2.2. Using constant specific heats, and use this value of Cp and Cv. Hey, did they give me the value of K? No, but all you have to do is take the ratio, and it'll be 1.4 for K. All right, determine and there's a bunch of things, but often all you really need to do is maybe get the thermal efficiency and mean effective pressure. But here I've added a bunch of additional intermediate calculations. So what is the temperature at the end of the compression stroke? How would we calculate that? Well, we're asked to find T2, and T2 divided by T1 is equal to a V1 divided by V2 raised to a power. Anybody remember that equation? It's assuming ideal gas, constant specific heats, undergoing isentropic process to the K minus 1 exponent. Yeah, right. And so what is this? This is our compression ratio. So T2 is equal to T1. In this case, it's 310 Kelvin raised to the compression ratio 20 to the 0.4 power. And you should get this temperature. How about the peak pressure? Well, where do we get the peak pressure? Are they asking me to calculate P2 or P3? If you look at your pressure volume diagram, is there a difference between P2 and P3? No, it's not. It's constant pressure heat addition. So you can calculate P2. Now, P2 divided by P1 is equal to V1 over V2 to some exponent. That's another one of those equations. What is the exponent on this one? Yeah, and so we would put in here that the pressure at the end of the compression stroke is a pressure at the beginning, 98 kilopascal, times the 20 compression ratio to the 1.4. How many people have a calculator? And do you verify that that is 6,496 kilopascal? 1, 2, 3, 4, 5. Perfect. Good. 6. Thank you. All right. So now we're pressing on. I recommend that when you start a problem like this, that you have your pressure volume diagram, your temperature entropy diagram. You have a table of properties. A table of properties. So for every state, 1, 2, 3, 4, you can put in the pressure or the temperature. If you want, you can put in specific volume if you like. But anyway, pressure and temperature at the minimum. And then a table of your transfers. What do you mean by the transfers? Energy transfers. So for the process 1 to 2, what is my Q? What is my W? For process 2 to 3, what is my Q, W? 3 to 4, and 4 to 1. Maybe I should have emphasized this for the diesel cycle. There's really 3 non-zero W's, where for the Otto there was only 2 non-zero W's. We had a negative work compression, 1 to 2. Then we have a positive 2 to 3. And then we have a positive 3 to 4. Those are 2 expansions. And then the last is 0. 4 to 1 is constant volume heat. Anyway, some students may miss that there's 3 terms for the work for the cycle. Okay. For the Q's, it's 0 and 0. This Q 2 to 3 is positive, and 4 to 1 is negative. But when you do the sum, that's Q net and W net, they must equal for the cycle. Okay. Once you have your diagrams, your table of properties, your table of energy transfers, then you can answer a lot of questions. But let's keep going. What is that peak temperature? How do I calculate peak temperature? What temperature is that? Isn't that T3? Yeah. How do I calculate T3? Well, knowing T2, I can continue to go, because what did we get? That V2 is equal to V3. No, that's not true. That was true for the Otto cycle. It's P2 is equal to P3. That's exactly right. And it always behaves as an ideal gas. So P is equal to RT divided by V, always. So we can substitute in here that we have T2 divided by V2 is equal to T3 divided by V3. So the highest temperature, T3, is T2 times V3 divided by V2. Have we seen that V3 divided by V2 before? Yeah, that's the cutoff ratio, isn't it? So it's just T2 times R sub C, our cutoff ratio. So 2.2, so this was T2 was 1027 Kelvin times 2.2, and a couple people, you get about 2260. Yep, okay, very good. How about the heat addition for the cycle? Now, again, this is a little tricky. I'm going to modify this. The heat addition for process 2 to 3. I don't want the net heat. I just want to know where's it coming in. It's only coming in the process 2 to 3, right? So Q 2 to 3, isn't that C sub P times T3 minus T2? Our C sub P was 1.005. Our T3 just calculated 2260 minus, and then 1027. Can some people run that number and see if you get around 1240? So there you go, that's Q. And again, you would be putting this down here, 1, 2, 3, 9. That's where I would be populating that table, like I would be populating these tables of temperatures and pressures. Okay, what is the net work for the cycle? How would I calculate the net work? Well, I can go back and calculate 3 things and add them up. That's one way. It'll work. Or I already have half of Q net calculated. Get the other half of Q net and know that Q net's equal to work net. That's a little more direct. And the book does that a lot. So when you do that, you'll find 790. Let me say that that's doable. Now, what is the thermal efficiency of the cycle? That's what we wanted, a large net work out divided by what we had to pay to bring into the cycle, Q2 to 3. So you take the 790 divided by 1239, and you get about 64%. So let me have a few people, assuming this number for part D and E are correct. What is this thermal efficiency? Do you calculate it 64%? 1, 2, 3, 4, 5, 6, good. And then the mean effective pressure. How do you calculate the mean effective pressure? It's W net divided by the displacement volume. So I have to get the displacement volume. How do I get the displacement volume? Kind of running out of room here. Let me scroll down. Displacement volume is V1 minus V2. Okay. Is ideal gas equation always valid? Sure. So I can replace V1, or how do I calculate V1? Would be RT1 divided by P1. Likewise, RT2 divided by P2. Is that one way to calculate the displacement volume? Remember, PV is equal to RT. Professor, is that R or R bar? Yeah, so you can put PV bar is equal to R bar T, or leave off the bars, and now it's how many meter cube per kilogram of the gas of interest. Here it's air. And then R is the gas constant for that gas of interest. So the relationship is, this is truly R up here, and that R is equal to R bar times molar mass, or divided by the molar mass of air? Yeah, divided by, and isn't the molar mass of air 28.97? Good to 4 digits. 28.97 kilograms per kilomole. Yeah. Man, there's a lot to remember from Thermo 1. Yeah, there is. Okay. So that finishes that problem. Here is some of the numbers. If you do all the calculations and then you just use our simple cold air analysis equation for the thermal efficiency of a diesel cycle with a given K and a given R and a given R sub C, you'll get the same answer. Here is it plotted. So here's state 1, here's state 2, state 3. You notice that there's a great pressure pickup, increasing at the end of it as you get to a smaller and smaller and smaller volume. Dramatic increase. And then this is the constant pressure heat addition, then the constant adiabatic isentropic expansion out to 4. So 1, 2, 3, 4. Yes, sir.
Is the displacement volume always V1 minus V2 this side?
Yeah. So here's V1 or V4, they're the same. And then this is V2. And so V1 minus V2 is the displacement, right? All right.